18th of September 1943. Pearl Harbor submarine base. Morning heat already thick. Lieutenant Colonel Frank Mercer stands in a maintenance bay holding a disassembled torpedo gyroscope. He is a naval ordnance specialist tasked with investigating why American submarines are dying from their own weapons. The problem has killed 17 men in 3 months. Torpedoes launched straight at enemy ships curve mid-run and circle back toward the submarines that fired them. Captains report the same pattern. Weapon runs true for 30 seconds, then veers in a wide arc. Some crews hear their own torpedo screws approaching through the hull before impact. Others surface to find their weapons circling on the surface, active and hunting. Mercer arrived from Washington 6 days earlier with orders to find the cause. He has opened 43 gyroscopes from weapons that malfunctioned or were recovered before firing. The pattern is clear now. The lubricant inside each gyroscope housing has broken down into a thin, separated fluid that no longer cushions the spinning mechanism. Without proper lubrication, the gyroscope drifts off its set course. The torpedo follows that drift into a circular path. The gyroscopes were designed in 1938 for North Atlantic operations. The lubricant specified in their blueprints is a petroleum-based oil that remains stable in cold water. It fails in the Pacific. Water temperatures here reach 85 degrees. The oil separates within hours of a torpedo being loaded. By the time a weapon is fired, its guidance system is already compromised. Mercer's immediate problem is supply. The original gyroscope design called for precision instruments manufactured in Sweden, using techniques developed for chronometers and navigation equipment. Those instruments are no longer available. Sweden is neutral but surrounded by German-occupied territory. No Swedish precision components have reached American forces since 1941. The gyroscopes now being installed in American torpedoes are domestic copies, built by manufacturers with no experience in temperature-stable lubricants. He spends 3 days testing alternatives. The Navy's standard lubricants all fail within 2 hours at tropical temperatures. Automotive oils break down even faster. Heavy greases are too thick. They prevent the gyroscope from spinning freely, causing the torpedo to tumble. What he needs is a lubricant that remains fluid enough to allow free rotation while maintaining its molecular structure under heat. On 21st of September, a chemist at the base laboratory suggests silicone-based compounds. These are new materials, developed in the last 5 years for high-temperature industrial applications. They cost 40 times more than petroleum oils. They are difficult to source, but they do not break down in heat. Mercer requests samples from 3 manufacturers. He receives the first batch on 24th of September. Testing begins immediately. He builds a heating chamber that maintains water temperature at 90 degrees, 5 degrees hotter than the worst conditions recorded in the Pacific. Gyroscopes are mounted inside, spun continuously and monitored for drift. The first silicone compound fails. It remains stable under heat but creates too much friction. The gyroscope slows and stops. The second compound works for 6 hours, then begins to separate. The third compound, manufactured by Dow Corning for aircraft engine gaskets, holds stable for 72 hours of continuous operation at 90 degrees. Mercer now has a lubricant that works. His next problem is sealing. The original gyroscope housings were designed with rubber gaskets that deteriorate in tropical conditions. Salt water seeps past the degraded seals and contaminates the lubricant. He needs a hermetic seal that will hold under pressure and temperature variation. He contacts a manufacturer in San Diego that produces sealed bearings for aircraft. They send a technician to Pearl Harbor with samples of their sealing system. Metal-to-metal contact surfaces with a thin gasket of neoprene synthetic rubber, compressed under spring tension. The system is designed for aircraft operating at high altitude where temperature swings are extreme. It should work underwater. On 29th of September, Mercer assembles the first modified gyroscope. Silicone lubricant inside a housing with aircraft-grade hermetic seals. He mounts it in a torpedo and runs a test firing in the harbor. The weapon tracks straight for 2,000 yards and hits the target barge within 3 feet of aim point. He runs 6 more tests over the next 2 days. All 6 torpedoes track accurately. No circular runs, no drift. The modification works. Now comes the harder task, implementing the solution across the Pacific Fleet. There are 42 submarines operating from Pearl Harbor, another 31 based in Brisbane, Australia, 17 more at Midway. Each submarine carries 24 torpedoes. Each torpedo contains a gyroscope that must be disassembled, cleaned, relubricated, and resealed. The work must be done by maintenance crews who have never performed this level of precision work. Mercer writes a training manual in 3 days. It is 16 pages long with detailed diagrams showing every step of the disassembly and modification process. He includes specifications for testing each gyroscope after modification, procedures for identifying contaminated lubricant, and troubleshooting guides for common errors. On 3rd of October, he begins training the first maintenance crew at Pearl Harbor. There are 8 men, all experienced torpedo mechanics but none familiar with gyroscope internals. He demonstrates the complete process twice, then supervises as each man performs the modification under observation. The work is delicate. The gyroscope mechanism contains parts machined to tolerances of 1/10,000th of an inch. A single fingerprint can cause contamination. Dust can jam the spinning assembly. 3 men fail the first attempt. Their seals leak or their reassembly is imprecise. Mercer has them repeat the process until they can complete it without error. By the end of the first day, all 8 men can perform the modification correctly. He certifies them as trainers and assigns each to teach another crew. The training spreads through the Pearl Harbor Maintenance Organization in 10 days. By 13th of October, 42 men are certified to perform the modification. They begin working through the torpedo inventory, processing 8 weapons per day per crew. Each modified torpedo is test-fired before being cleared for combat use. Mercer flies to Brisbane on 16th of October. The Australian base presents different challenges. Supplies are harder to obtain. The silicone lubricant must be shipped from the United States. Sealing components must be manufactured locally using specifications Mercer provides to Australian machine shops. He trains the first Brisbane crew on 18th of October and establishes the same training cascade he used at Pearl Harbor. Quality control becomes critical as the modification program expands. Mercer establishes a reporting system requiring each maintenance crew to document every modification with serial numbers, test results, and crew signatures. Any torpedo that fails testing must be disassembled and inspected by a certified trainer. Any crew that produces 2 failures is retrained from the beginning. The first combat results arrive in early November. The submarine USS Wahoo reports successful attacks on 3 Japanese cargo ships using modified torpedoes. All weapons tracked accurately. No circular runs. Captain Dudley Morton sends a message to Pearl Harbor. Torpedoes running true. Crew confidence restored. More reports follow through November. Submarines that had avoided firing torpedoes due to circular run risk now engage targets aggressively. Hit rates improve. Japanese shipping losses increase. The modification program proves its value in sunk tonnage. By 25th of November, circular runs across the Pacific Fleet have dropped from 11% to 2%. The remaining failures are traced to improper maintenance procedures or contaminated lubricant batches. Mercer issues updated quality control protocols and arranges for lubricant testing at each base before it is used. The final implementation challenge is sustaining the program as new submarines enter service and new maintenance crews require training. Mercer establishes a certification system requiring annual retraining for all torpedo mechanics. He arranges for silicone lubricant to be included in standard supply shipments to every submarine tender and base. He writes technical bulletins distributed to every maintenance organization in the Pacific, documenting common problems and solutions. By December 1943, the torpedo reliability crisis is over. American submarines operate with confidence in their weapons. The blockade of Japan intensifies. Japanese cargo ships carrying oil, rubber, and raw materials from Southeast Asia are sunk faster than they can be replaced. By mid-1944, Japan's industrial production begins to collapse from lack of resources. Mercer returns to Washington in January 1944. His emergency modification program has been formalized into standard procedure for all American torpedoes. The silicone lubricant and hermetic sealing system become permanent features of gyroscope design. The training protocols he developed are adopted across all naval ordnance maintenance programs. He receives no public recognition. The torpedo reliability problem is classified. Its solution is classified. The reports documenting circular runs and the deaths they caused remain sealed in Navy archives. Mercer's work is known only to the submarine force and the maintenance crews who implemented his modifications. He is reassigned to torpedo development in March 1944, working on next-generation guidance systems. He remains in that role through the end of the war, ensuring that new designs incorporate the lessons learned from the Pacific crisis. The circular run problem never returns. Post-war analysis credits improved torpedo reliability with a 37% increase in Japanese shipping losses during 1944. Those losses directly contributed to Japan's inability to sustain its war effort. Oil shipments from the Dutch East Indies dropped by 80%. Rubber and metal imports collapsed. By early 1945, Japanese factories were shutting down from lack of raw materials. Mercer's solution to a mechanical problem, temperature-stable lubricant and hermetic seals, enabled the strategic blockade that starved Japan's military machine. His training program, implemented in 10 weeks across dozens of bases and hundreds of maintenance personnel, transformed an unreliable weapons system into the most effective tool of the Pacific submarine campaign. He retired from the Navy in 1946 as a full colonel. He died in 1967. His obituary made no mention of torpedoes or the Pacific War. The files documenting his work were declassified in 1973. 26 years after the problem he solved had ceased to matter to anyone, except the submariners whose lives depended on weapons that ran straight and true.